Huawei is very dangerous.
Rarely does a country go to war with a private company.
We have met the enemy, and it is Huawei.
We're not going to do business with Huawei.
Huawei represents a national security risk.
But is this really about Huawei? Or is it something bigger than that?
December 6th, 2025. A patent filing surfaces that makes semiconductor executives around the world stop breathing. Huawei, the Chinese tech giant that's been locked out of advanced chip-making equipment since 2019, just published a detailed blueprint for manufacturing 2-nanometer chips. The same cutting-edge technology that TSMC, Samsung, and Intel have invested over $100 billion developing, except Huawei claims they can do it without the $150 million machines they're banned from buying. To understand why this patent is seismic, you need to understand the technological cage Huawei has been trapped in. In 2019, the United States banned Huawei from purchasing chips manufactured by TSMC in Taiwan. Then, in 2022, the Netherlands blocked ASML, the only company on Earth that manufactures EUV lithography machines, from selling to China. These EUV machines are the absolute gatekeepers to advanced semiconductor manufacturing. They cost over $150 million each, require operation in a vacuum, and use light with a wavelength of 13.5 nanometers to etch microscopic patterns onto silicon wafers. Without EUV, the entire semiconductor industry believed you simply could not manufacture chips below 7 nanometers. This was considered fundamental physics, not a technical challenge, but an actual barrier. Only TSMC, Samsung, and Intel possess these modern EUV machines, giving them an insurmountable advantage in the race toward 2-nanometer and 3-nanometer process nodes. But here's where Huawei started breaking the rules everyone thought were unbreakable. In 2023, they released the Kirin 9000's processor, a 7-nanometer chip that wasn't supposed to exist. Western analysts had written off Chinese chipmaking as stuck at 14 nanometers or worse. Then, in 2024, the Kirin 9030 pushed toward 5-nanometer equivalent performance. Each time experts said impossible, Huawei and their manufacturing partner SMIC proved them wrong. They were doing this with older DUV lithography machines, deep ultraviolet technology that uses light with wavelengths of 193 nanometers, or 248 nanometers. To put this in perspective, that's like trying to write with a marker that's 10 times thicker than the lines you're trying to draw. The physics shouldn't allow it. Yet, somehow they're making it work. Now, this patent filed back in June 2022, but only published on December 6, 2025 by China's National Intellectual Property Administration, lays out their roadmap for 2-nanometer manufacturing. The document is titled Metal Integration Method for Manufacturing Integrated Devices, and it describes something called self-aligned quadruple patterning, or SAQP for short. Instead of using EUV to draw ultrafine patterns in one exposure, Huawei's method uses DUV machines to build up the same patterns through multiple carefully orchestrated steps. Think of it like this. EUV is drawing a thin, precise line with a fine-tip pen in one stroke. SAQP is drawing that exact same line by making 4 separate passes with a thicker marker using stencils and spacers to guide each pass with atomic precision. The patent specifically describes using 5 spacer layers and multiple metals including ruthenium, copper, and cobalt to create self-aligned metal interconnects spaced less than 21 nanometers apart. The brilliance and the gamble of this approach becomes clear when you look at the numbers. TSMC currently achieves yields of around 90% on their 7-nanometer process using EUV technology. That means out of 100 chips they manufacture, 90 work perfectly. SMIC using DUV multi-patterning for 7-nanometer chips achieves only 50% yields. At 5 nanometers, their yields drop to around 30%. This has massive cost implications. Each Chinese manufactured chip currently costs approximately 40% more than an equivalent chip from TSMC, even with Chinese government subsidies covering roughly 30% of manufacturing costs. Now, imagine pushing this complex multi-patterning process to 2 nanometers. Each additional processing step is another opportunity for defects. A single speck of dust, a microscopic temperature variation, a chemical impurity measured in parts per trillion, any of these can ruin an entire wafer. Industry analysts estimate that initial yields for 2 nanometer chips using this method could be as low as 10 to 15%, making each successful chip extraordinarily expensive. So why would China accept these astronomical costs? The answer is written in the language of technological sovereignty. The Chinese government has poured tens of billions of dollars into semiconductor independence, viewing it as a matter of national security rather than simple economics. This isn't about making the most profitable chips today. It's about ensuring that in 10 years or 20 years, China isn't held hostage by foreign technology restrictions. The state can subsidize inefficient production indefinitely if it means achieving self-sufficiency in the most strategically critical technology of the 21st century. Let's compare Huawei's approach directly to what TSMC is doing. TSMC's 2 nanometer process entering mass production in 2025 uses advanced EUV lithography with high numerical aperture optics and gate all-around transistor architecture. They've spent over $40 billion on research and development and new fabrication facilities. Their approach is proven, reliable, and will likely achieve 85 to 90% yields from the start. Huawei's path uses older DUV equipment that Chinese companies can still access, combined with extraordinarily complex multi-patterning techniques. It's riskier, more expensive per chip, and unproven at scale. But if it works, it doesn't require the $150 million machines that China is blocked from buying. The geopolitical implications ripple far beyond semiconductor specifications. TSMC controls approximately 60% of the global foundry market and nearly 90% of advanced chip manufacturing. Their customers include Apple, Nvidia, AMD, Qualcomm, essentially every major technology company. If Huawei successfully manufactures competitive 2 nanometer chips, even at higher costs, they could supply China's enormous domestic market. That's 1.4 billion consumers. Companies like Xiaomi, Oppo, Vivo, BYD, Alibaba, and ByteDance, plus government and military applications. We're talking about potentially 30 to 40% of global semiconductor demand shifting to Chinese foundries. For TSMC, losing access to Chinese customers would represent a massive revenue hit and could fundamentally reshape the global chip industry into 2 parallel ecosystems. But here's the critical reality check. Having a patent is one thing. Manufacturing millions of flawless chips is entirely different. The patent shows serious engineering work and genuine innovation, but it's not proof of production capability. We have no evidence yet of actual 2 nanometer chips being manufactured at any scale. The timeline from patent to mass production typically takes 5 to 7 years minimum, potentially longer for such a complex process. Huawei would need to build an entire ecosystem of ultra-pure chemicals, specialized photoresists, advanced inspection equipment, and thousands of trained engineers who understand these processes. TSMC spent 30 years and worked with over 600 suppliers globally to build their capabilities. Meanwhile, reports emerged in early 2025 that China was testing its own extreme ultraviolet lithography machine at Huawei's Dongguan facility. Trial production was reportedly scheduled for the third quarter of 2025, with mass manufacturing targeted for 2026. If successful, this would shatter ASML's 100% monopoly on the most critical technology in the semiconductor industry. The machine uses an entirely different approach called laser-induced discharge plasma, or LDP, compared to ASML's laser-produced plasma method. Instead of firing high-energy lasers at tin droplets requiring complex control systems, the Chinese system vaporizes tin between electrodes and converts it to plasma through high-voltage discharge. Industry insiders claim this approach offers a simpler architecture, smaller footprint, better energy efficiency, and potentially 30 to 50% lower production costs. So is TSMC actually in trouble? Not in the next 2 to 3 years, Their technology leadership is secure. Their customers aren't going anywhere, and they're already shipping 2-nanometer chips to Apple and others. But the conversation has fundamentally shifted. What seemed impossible, advanced chips without EUV, is now merely improbable. And Huawei has a track record of making the improbable real. The 7-nanometer Kirin 9000s wasn't supposed to exist. The 5-nanometer equivalent Kirin 9030 defied predictions. This 2-nanometer patent might be the next chapter in that story, or it might join countless ambitious patents that never escaped the laboratory. Either way, the semiconductor war just entered uncharted territory, and the next 24 months will tell us which future we're headed toward. In the semiconductor war, the rules everyone thought were unbreakable keep getting broken, and that might be the most important story in tech right now.